Colby.
And I'm Connor Smolinski.
And this is an introduction to spectrophotometry of absorbance of cobalt-2 chloride.
The purpose of our experiment, the layout of our presentation. First we'll discuss the purpose of our experiment, and then we'll give an introduction which will conclude several definitions and equations. Then we will go over our experimental, which will give a concise procedure of the experiment. Following that, we will go through our results section, which includes tables and figures containing the data that we collected, which include examples of those calculations. After that, we will discuss our discussions and conclusions, which contain our final conclusions regarding the experiment. And following that are our references.
The purpose of our experiment was to determine the absorbance of cobalt-2 chloride. We wanted to create a standard curve and spreadsheet using the data. And using the data, we wanted to determine the unknown concentrations that we were given.
First, we'll give some definitions before we go into the experimental. Spectroscopy is the identification of properties using the absorbance spectrum. Spectrophotometry uses radiation in the form of light to determine the amount of substance. The amount of light absorbed is dependent on the amount of substance that is present. And this is used to measure absorbance and percent transmittance.
Throughout this experiment, we used Beer's law equation, which is absorbance equals epsilon times concentration times path length. And the higher the concentration, there's more light was absorbed. Epsilon was just proportionality constant, which is more absorptivity. C was molar concentration of substance, and L was just the path length, or how far the light would travel through the solution. And this right here is just like a diagram just showing how concentration and absorbance relate to each other on the standard line.
Absorbance can be specifically determined using this equation, where A equals absorbance. Absorbance is equal to 2 minus the log of the percent transmittance. The percent T, or percent transmittance, is the percentage of light that travels through the sample that you're working with. These equations were essential for finding the unknown concentrations that we were working with.
For our experimental, we had first obtained 2 microvets, and we set the spec 20 to 400 nanometers. One cuvette was filled with deionized water, like 3/4 away, and the other is 3/4 away filled with cobalt-2 chloride at 0.105 molar, 0.150 molar. And the water cuvette was placed in spec 20 to calibrate it, and from there we record the percent transmittance absorbance from 400 nanometers to 600 nanometers with 25 nanometer increments. And we did this for every sample where we recalibrated, putting the water blank in. And then we put the cobalt-2 chloride in to determine the percent transmittance and absorbance. And from here, we got the lambda max was determined because absorbance was the highest and the percent transmittance was its lowest.
Then we made a set of dilutions from the standard to make the standard curve. 8 test tubes were used in total, and the first tube was our control, which was filled with 5.0 milliliters of deionized water. Test tubes 2 to 7 were dilution sets, which contained different amounts of DI water and cobalt-2 chloride. The final tube was 5.00 milliliters of cobalt-2 chloride.
We then recalibrated spec 20 with the blank. Absorbance percent transmittance of dilutions were measured. Concentrations determined using the molarity equation, which is MC times VC equals MD times VD. Standard curve is created using this data, and the standard curve showed the relationship between the concentration and the absorbance.
We used our standard curve to find the best fit line of the equation. And this equation was used to determine the concentrations of our unknown. And the equation can be translated to Beer's law, which is absorbance equals epsilon times wavelength times concentration plus V.
Here is a determination of lambda max, the construction of the absorbance max spectrum of cobalt-2 chloride. This table will show the calculated absorbance and percent transmittance of cobalt-2 chloride from 400 nanometers to 600 nanometers. And you can see as percent transmittance was lowest at 17, and absorbance was 0.772, which is the highest in its column, and that gave us our lambda max of 500 nanometers.
This is an example calculation for absorbance. We used the absorbance equals 2 minus log of percent transmittance equation. We substituted 84.0 into the equation and got an absorbance of 0.0757. This was calculated at 400 nanometers.
Here's our absorbance spectrum of cobalt-2 chloride, and this figure showed how the wavelength and absorbance were directly related, how absorbance was its highest. And when that absorbance was highest, we had the wavelength of 500 nanometers, which was our wavelength.
This is our table 2, which shows this was whenever we were trying to construct our standard curve. The column on the, the column on the left shows the volume of the molarity of cobalt-2 chloride, which ranges from 0.00 milliliters to 5.00 milliliters. And following that is the volume of DI water, which goes from 5.00 milliliters down to 0.0 milliliters. Then the concentrations of our molarity, which vary depending on the dilution that we were using, along with the percent transmittance and the absorbance at the lambda max, which were determined through our dilutions.
On the left, we have an example molarity calculation for test tube 3, and we use the MC times VD equals MD times VD. Our MC was our molarity of cobalt-2 chloride, which is 0.150 molarity. And our 2 milliliters was our VC, which is how much cobalt-2 chloride we added into the dilution. We were solving for MD, and VD was 5 milliliters, which is our total solution. And solving for that, we got 0.0600 molarity. And on the right, we have an example epsilon calculation for test tube number 3. The original equation is absorbance equals epsilon times concentration times path length. And we rearrange that equation to make it epsilon equals absorbance divided by concentration times path length. And just plugging in our information, we got epsilon equal 5.47 liters divided by molarity per centimeter.
This is figure 2, which shows our standard curve. From the standard curve, we obtained the equation y equals 4.6361x plus 0.0138, which we use to solve for the molarity, the concentration. The concentration.
Here is the determination of our concentration of unknown solutions, where we determined our unknown concentrations at lambda max of 500 nanometers. For our unknown 12, our percent transmittance was 36, and our absorbance was 0.446. And for unknown number 13, our percent transmittance was 31.6, and our absorbance was 0.500.
This is an example calculation of our concentration. This is item number 12. We used the y equals mx plus v and changed it to Beer's law. Absorbance equals sigma times path length times concentration plus v. After plugging in all of our data, we were able to determine that the concentration of unknown 12 was 0.0932 molarity.
And the same thing, we got unknown 13. We use y equals mx plus b from the standard line in our Excel PowerPoint. And we rearrange that to be absorbance equals epsilon times path length times concentration plus b. And just plug in our information off the Excel, we were able to get concentration to be 0.105 molarity.
For our discussion and conclusion, we determined that the percent transmittance and absorbance have an inverse relationship. This was shown in table 2. As percent transmittance decreased, the absorbance increased. Another example of this in test tube number 1, the percent transmittance was 99.4, and the absorbance at the lambda max was 0.00300. In test tube number 2, the percent transmittance was 69.4, and the absorbance at the lambda max was 0.158. And here is table 2, where you can see here where the percent transmittance was 99.4, and the absorbance was 0.00300, and same here, 69.4, the absorbance was 0.158. As the percent transmittance decreased, the absorbance increased.
Question 2, our data did support lambda max of 500 nanometers. The table 1 was the highest absorbance of 0.772. At lambda max, which was the percent transmittance there, was 17, which was its lowest, and the absorbance was 0.772, which was its highest. And the unknown concentrations did fall in the linear regression line, figure 2. And our unknown solutions fall right here, because we got our y equals mx plus b formula, and this just shows the direct relationship between concentration and absorbance. As both go up, the other both go up, actually.
We found out that the absorbance and concentration had a direct relationship. This is seen in table 2. When the concentration increased, so did the absorbance. In test tube number 6, the concentration was 0.105 molarity, and the absorbance was 0.410 molarity. In test tube number 7, when the concentration increased to 0.120 molarity, the absorbance also increased to 0.506. And this is in figure 2, you can see where the heck is that? Okay. Right here. 0.05 molarity here, and it increases, the absorbance goes to 0.410, and when the concentration increases to 0.120, the absorbance increases to 0.506.
So our question 3 continued. We did support Beer's law because absorbance and concentration were directly related. As concentration increased, so did absorbance, and less light was able to pass through. And our unknown 12 concentration was 0.0932 molarity, and our unknown 13 was 0.105 molarity.
We determined the purpose of this experiment was to determine the lambda max of cobalt-2 chloride. We found that lambda max to be at 500 nanometers. As the percent transmittance decreased, the absorbance increased, and as the concentration increased, the absorbance increased as well. These are the trends that we discovered during our experiment. We determined our unknown concentration of unknown number 12 to be 0.0932 molarity, and the concentration of unknown number 13 to be 0.105 molarity.
These are references. Thank you.